All right, picking up where I left off. Again, going quickly, pause video if you need to and go back. This one says, in which section did the animal travel the greatest distance? And again, look at your y-axis. This is distance. So the up and down changes is a change in distance. So the biggest line, the line segment that has the greatest change up and down at any point is T, because it goes from this point to this point. Again, you can measure that distance up and down. Didn't ask us for how much that was. It just asked us which one had the greatest one. So we're looking for the biggest change up and down. Next set of questions, again, you may have had them randomly if you took the quiz. This one says, what's the total distance traveled? So again, to do total distance traveled, we simply need to add up all of the line segments in terms of how they're going up and down. Again, the y-axis is telling us the distance. So we start at 10 and go up to 30, that's 20. And then we go back to 10, that's another 20. We go from 10 to 40. Again, I'm just looking at the y-axis. So up 20, down 20, up 30, and then back down 40. So if we put all that together, 20 plus 20 is 40, plus 30 is 70, plus 40 is 110. So the total distance is 110 yards. The next question is asking about displacement. Again, displacement is snapshot at the beginning, snapshot at the end. How much did I change? At the beginning, we're at 10 yards from the starting line. At the end, we're at the starting line. So our displacement, if we want to be technical, is negative 10, negative 10 yards or 10 yards to the left. Again, the zigzag part, none of that matters. It's just where did I start and where did I end? That's what displacement is. The next two questions followed up on that. Speed, by definition, is distance divided by time. Right? So speed is distance over time. Distance we've already calculated was 110 yards. The time is on the graph. It was 4 seconds. And so put all that together, and we should have had 27.5 yards per second is the math and the way the math comes out on that. The next problem was about average velocity. Velocity uses displacement if we're doing average velocity. And we've already calculated and shown that the displacement, again, we do displacement divided by time. So in this case, the displacement was 10 yards left or negative 10 yards, and the time, again, was still 4. And so the displacement could be, or excuse me, the velocity would be 2.5 yards per second. And we could write this 2.5 yards per second to the left because, again, up on a graph like this, up is considered positive, which would also mean to the right, and going down is considered negative or back to the left. And so we could say 2.5 yards per second to the left. You could also say just negative 2.5 yards per second and not put the left. The negative sign could indicate the direction as well. So you could actually put a direction or you could use positive or negative. Next question was asking how fast was the motion at 2.5 seconds? How fast something is distance divided by time. Again, this graph, if you go back to your formula sheet, speed is distance divided by time. On this graph, I've got distance, and on this graph, I've got time. So at 2.5 seconds, when we're about right here, I'm on this line segment, which means that since this slope is constant, that tells me that my speed is constant. So anywhere on this line, I have constant forward motion, which means the speed anywhere on this line is going to be the same. I can take 2 points on the line and figure out my slope. Again, slope is rise over run, which is, again, change in distance divided by change in time, even if you can't remember that. So from this dot at the beginning of C to the dot at the end of C, I go up 30 and I go over 1. So the speed in this case is going to be 30 yards per second. So everywhere on this line, the speed is 30 yards per second. So in summary, to get the speed of a point, you need to get the slope of the line that is on. Distance divided by time gives us the speed. And acceleration means that we are speeding up, slowing down, changing directions. So if we look at all of these, graph 1, distance is increasing constantly. That's not a change in speed. Graph 3, distance is going backwards constantly. That's not a change in speed. Graph 2, there is no motion. That's not an acceleration. Graph 3 is we are increasing our distance and the slope changes, which means that this is not a constant change. So the curvature on this graph is telling me that the distance is not changing equally. So in this case, it's actually speeding up. Next two problems were kind of the same problem, but with speed and velocity. So to answer the speed question, we need distance divided by time. To get velocity, we need displacement divided by time. So in this case, it helps to draw, I think, sometimes. So we're going 40 meters, and it takes 20 seconds. And then we go back 20 meters, and it takes 10 seconds. To get the speed, I add everything up. So my total distance traveled was the 40 plus 20, so it's 60. The amount of time that we took was 20 plus 10, so I got 60 over 30, and that's going to equal 2 meters per second. Don't need a direction. Velocity, again, uses displacement. So because these are going in opposite directions, they have opposite velocities. And so we have to take all of that into account. So instead of 40 plus 20, it's going to be 40 minus 20 because we're going back in the opposite direction. So our displacement was 20. We're 20 units right, or plus 20 units to the right, however you want to indicate it. The time is still the same, which is going to be 30. So in the calculator, 20 divided by 30 is going to be 0.67. And again, still meters per second. And you could indicate that with a positive. You could indicate that with a right. Either of those would be fine. And with this one, very last one, I'm not going to go through and do all the math with it. But in the case of each one of these, if we want to know which one was the slowest animal, we simply need to do that. Speed is distance divided by time. So for each one of these, you've got a distance, you've got a time. So you could put these into your calculator, distance divided by time, and get a speed. Distance divided by time, and get a speed. And I think if you do the math on this, the giraffe ends up being slowest because it's going to have the smallest number. All right. So again, smaller the number, slower the speed. Higher the number, the greater the speed. So again, distance divided by time is going to give us the speed on that one. And that is it.